Hi everyone. Today we present our paper, X, Sparsity-Specific Code Generation. This paper is a joint work with Teseo Schneider, Shoaib Kamil, Aurojit Panda, Jinyang and Daniele Panozzo. Sparse matrix computations are commonly used in applications that exploit structure, from social network to Laplacian matrices. Hence, they can be seen in many applications like machine learning, parametrization, and deformation. In those applications, normally a connectivity list is given in some format, from which one can derive a connection matrix, which is normally sparse. Then, the edge weights will be plugged into the matrix for further computation. Because of the sparsity, those matrices are stored not like a dense matrix. Instead, there are two major ways to store a sparse matrix: compressed sparse row and compressed sparse column. Both of the storage formats rely on three arrays to store the position of the non-zero elements and the values. Due to this storage format, computation performed upon sparse matrices are also quite different from the dense ones. For a simple sparse matrix multiplication, an algorithm will traverse the arrays multiple times to find collisions, which result in horrible memory usage. Recently, there are many libraries implement and optimizes sparse computations. Among them, the most popular ones are Eigen, Intel's math kernel library, and the tensor algebra compiler. Eigen is well known and widely used due to their user-friendly interface. In order to do sparse computations, they implemented common binary and unary sparse operations. To support composite expressions, they do an evaluation at each level of computation. However, Eigen's performance is quite bad, and this is also well known. MKL, on the other hand, optimized further on common operations such as A times B, ATDA, etc. However, it does not support doing composite expressions in one go. Instead, user has to get the result from each expression, then further propagate the result for the next operation. Taco's strategy is to ask user to define the operation in storage format, then generate a piece of code that optimizes the performance. But at the moment, the sparse operations are not supported yet. All of those methods aim to optimize single operations by strategies like better memory usage, plus operations, etc. However, they ignore an important feature, that for many of the sparse applications, if the matrix is assembled through some structure, the sparsity pattern remains the same throughout the execution and only the value will change. This means that exactly how and where the collision will happen is fixed, and the sparse structure can be discarded after the first computation. Introduce X. X targets applications where sparsity remains the same throughout the execution. It can be plugged into existing Eigen code easily, supports single-entry definition which makes stencil operations possible. It will generate and compile code for specific sparsity and operations when needed. The code is automatically linked to the current application. User does not have to do extra work. The code also supports AVX and SSE instructions and are also auto-parallelized. All of those result in fast sparse computations. So how does it work? First, we create the symbolic version of the matrix by converting the data type. Note that during this execution, the value information is lost since we only care about the structure. Our data type saves two things: the matrix ID, which is in which order you will pass the matrix value, and the data ID, which is where the entry lies in the value array in whatever storage format you pass in. Here, we're using CSR so you see the data ID are ordered by rows. Next step, the user will do operations directly on the converted matrix. Say, if we want to do matrix multiplication, we rely on Eigen itself to perform this operation. In the result matrix, there will be operation trees at each non-zero position. Notice that the operation tree does not care about the numeric value, but only the operation itself and where to fetch the data for numeric computation. We then look at the value array of the result matrix and check for the variation of operation trees. In this particular example, we find one unique operation tree. This tree multiplies two elements. The first element is from matrix 0, and the second element is from matrix 1. An operation tree does not care about the data ID at this step, but only the matrix ID. With the tree information, we can generate the code specific to this operation and sparsity, which is shown on the right. The data IDs are then reordered in such a way that the ones with the same operation trees will be executed together. The result positions are just the indices for where to store the computative values in the result array. Note that we copied the last operation tree twice. This is just to make sure that AVX instructions are executed correctly, since they normally require 2 values per instruction. With the reordered data ID and the result positions, the code can be used to produce the correct result. Each time, we get 2 elements from matrix 0, 2 elements from matrix 1, do the multiplication, and store back. At this step, the code will be compiled and linked to the application. We can now plug in the values from matrix 0 and matrix 1 for final computation. But what does the code look like for this example? Well, in Eigen, it is easy. You prepare the sparse matrix, and you multiply them. In MKL, we need to convert the matrix into MKL sparse type. Declare the variables that will be used later on, then do the 3-level computation. First, non-zero counts. This allocates storage for the result matrix. Second, compute the structure. At the step where the collision will happen and how it will happen should be known. Third, numeric execution. This is where you get the final value. You can substitute the values in the 2 matrices and still get the correct result, given that you do not touch the matrix structure. Then, what does it look like in X? After you prepare the matrix, you need to first convert the data type. Second, do whatever operation you want to do with the original matrix on the converted matrix. Third, simply use our interface to analyze and generate the code specific to this operation and sparsity. Then, allocate some space for the input and output. Lastly, assign the values to the input and call the executor. The results will be in the results array. If you want to change the value of the input, simply assign the value to the data array. But what if you want to do a times b plus b? With Eigen, you simply do plus b. With our method, you just do plus b numeric, and the others remain untouched. But in MKL, you will need to get the results from a times b, then do extra steps to get plus b. We will not show the code here due to the size of the slide. Now we will show some results. We tested our performance on some common operations. Here, we will show ATDA, where A is a sparse matrix and D is a diagonal matrix. The test matrices vary in size, but all have on average 5 entries per row. As expected, Eigen is quite slow compared to our method. On average, we see a 25 times speedup in single-thread performance. This difference, depending on the application, can shift the bottleneck from computation to something else, which we will show later on. Next, we compare against MKL on the same operation and see an 8 times speedup on single-thread performance. Since both MKL and X support multi-threading, we further run the same example with 8 threads and see a 10 times speedup over MKL in this test. Furthermore, our method has a better scalability than MKL in this test. We also tested on some composite expressions. Here, we show one of the expression of alpha A plus B transpose times beta B transpose plus C, where A, B, and C are sparse matrices, and alpha and beta are numbers. Comparing to Eigen, we see an 18 times speedup. Comparing to MKL single thread, we see an 1.8 speedup in such operation. This is not as good as the single expressions we showed before, and is due to the fact that we do not compute intermediate results and try to do everything in one go. We'll explain it later on in the limitation section. With multi-thread, we see around 3 times speedup compared to MKL. However, in real world, applications usually involve more than just sparse computations in execution. We look into libIGL for such cases. In this example, we're computing a parametrization, which needs to do a minimization of energies and requires a computation of ATDA plus B for right-hand side, where A and B are sparse matrices and D is a diagonal matrix. We integrated our method as well as MKL for sparse computation, which is the green part in the graph. Compared to the original Eigen implementation, the green bar of our method is barely visible. Note that although the subpart is the same for every method, our optimization in computation brought an overall 3 times improvement on the runtime of the whole algorithm and makes the bottleneck no longer the compute, but solve. Next, we use the same strategy on volume mesh deformation and see a 5 times overall speedup compared to the original Eigen-based implementation. This application is usually interactive, and our speedup allows a single iteration to complete in 0.36 seconds instead of 1.8 seconds, reducing the time the user has to wait to see a preview of the deformation. We also use our strategy in cotangent smoothing, which needs a sparse computation of LTML plus WM, where L is a sparse matrix and M is a diagonal matrix. In this example, we see a 2 times speedup on the entire execution against Eigen and a 1.1 times speedup against MKL. Furthermore, since our method supports per entry definition, we also use our method to optimize cotangent matrix assembly in libIGL. In this example, we see a 4 times speedup on large mesh and 2 times speedup on small mesh. We also compare to PMP's implementation of cotangent matrix assembly, which is highly optimized by hand, and see that we're not that far behind. Last, we implemented obstacle flow, a method that requires a sparse matrix assembly where entries are defined by stencil operations. However, due to it being a regular grid, the solve takes forever and largely outweighs the speed gain we had over the computation. Overall, we see a 1.1 times improvement for the entire execution. Now, what are the limitations of our method? Although X can detect repeated operations within the same tree and mark it as the repeated operation, when it comes to global repeated operations, X does not detect them at this stage. As a matter of fact, early experience shows that if we do one level of menu optimization by computing intermediate results in the cotangent matrix assembly example, we can have another 4 times speedup, making us faster than PMP's implementation. Another limitation is the pre-computation speed. Our method has 4 stages: symbolic execution, analysis, code generation, using Ninja template engine, and code compilation. While the first 2 stages are generally fast, the last 2 stages can be slow depending on how complicated the operation trees are, how many unique operations there are, and how long the code will be. This sometimes results in really long pre-computation time if the matrix is small and dense. In the future, we plan on 3 paths for this project. First, as discussed, global repeated operations can lead to more computation. We plan to eliminate such computations by explicitly computing them first and reuse the result in the execution. Next, since we flatten our operation tree and store the nodes in a vector where each entry takes 56 bytes, it can lead to large memory consumption during the pre-computation phase. We plan on optimize such memory usage later on. Lastly, our current implementation only generates code for CPU execution at the moment. However, we believe that the code generation technique can be directly used to generate GPU code. For more technical detail and results, please view our paper. The code for this paper is public and can be found on GitHub. We thank you for your audience.